students. So today we are continuing thermal properties of matter. In this session we are going to start the topic heat transfer. Okay, so the topic coverage of thermal properties of matter, initially it is all about thermometry. From thermometry we will come to thermal expansion. From thermal expansion we move to calorimetry. Last main topic, okay, it is heat transfer. Okay, so heat transfer is all about how heat is transferred from one point to another point. Okay, so there are various modes are there, so that is the reason we are studying this separately. Okay, so there are three methods, or there are three ways for the heat to transfer. Okay, so three processes are there based on the condition. Okay, first one is conduction. Okay, so first one is conduction. Okay, so conduction, mainly the transfer occurs through the vibrational energy of the atoms and molecules. Suppose just for our understanding, suppose if these three are molecules, then suppose if this one here we are supplying heat here. So when this molecule or this atom gets heat, its vibrational energy will increase, it will start vibrating. When it vibrates, definitely it is going to hit this, collide with this. So this also will vibrate, and this one will vibrate and hit this atom, and that also will be vibrate. So through this vibration, or through this energy transfer occurs through the vibrational energy of the molecules. Okay, so heat transfer occurs through a vibration of the molecules. Actually those molecular transfer will not happen, that is the material will not come, or the matter will not get transferred, only the energy is transferring in this conduction. Okay, so one by one we will see, then we will concentrate on each thing. Okay, okay, so first one, due to vibrational energy of molecules. Okay, due to vibrational energy of molecules. Which one? Conduction. Okay, next one is convection. Okay, not only this point, another points also we will discuss. First we will just get an introduction. So in convection, actual movement of the molecules will occur. So this is mainly due to density difference. Suppose if one place, if the temperature is more, the density will be less. So from the other point, molecules will come to this place. Okay, when density goes down. So here this one mainly in liquids. Okay, so we can say actual movement of molecules. Actual movement of molecules. Okay, third one is radiation. Okay, in radiation, energy transfer occurs without any medium. Okay, here medium is there, that is the reason vibrational energy is there. Here also medium is there, that is why the actual movement of molecules will happen. So here without medium. Okay, so energy transfer occurs without any medium. Okay. Now this one, in this conduction occurs mainly in solids and in mercury. Okay, mainly in solids and mercury. Okay, mainly in solids and mercury. So here this one is actually mainly in liquid and gas. Okay, mainly in liquid and gas. Okay, so for this one nothing is required. Again, no medium, nothing is required. Clear? Note it down. Okay, so here one point I would like to add. So when I say conduction due to vibrational energy of molecules, this is actual movement of molecules, but here we can add one more point, like we can say like electromagnetic radiation. Here movement occurs through electromagnetic radiation. You can say electromagnetic waves or radiation. Okay, so that we can write there. Okay, now here we can say in conduction heat transfer occurs due to temperature difference. Okay, here heat transfer occurs due to temperature difference, due to temperature difference. Okay, due to temperature difference. So in conduction we can say, suppose if we use a spoon and if you do something in kitchen, right? So suppose if we do something in kitchen, you might have seen your mom and even you might have done this. Okay, if you're using a spoon, if we do our work in kitchen, if we are dipping the spoon in some hot tea, if you are making tea, then if you have dipped it slowly, after some time when you touch this end, it will be hotter. So there the main reason is what? Conduction. Okay, note it down. So this is mainly due to temperature difference. Okay, what about this one here? Due to density difference. This is due to density difference. So thing is, I already told you, when temperature at one area, suppose if this is, consider this area, if I increase the temperature of this area, the air molecules, it will expand, its density will come down. So here density will be comparatively more, so here more pressure will be there, it will move to this side. So here the temperature was more, here the temperature is less. Now what will happen? This will come to this side and it will maintain the temperature equal. Okay. Okay, what about this one? This is actually the one example for this one. Radiation is without any medium, it is just propagating. It will propagate in all the directions. Suppose if the temperature of a body is more than its surroundings, then it will start emitting radiations. So we can say here again, temperature difference. Temperature difference is the reason, but one thing which we need to be careful here, it is, even though temperature difference is not there, Suppose if we are a body, we have a body, we will be absorbing some radiation, we will be emitting some radiations parallelly. Okay, both these processes are happening together. Okay, so even though temperature is same, this process will happen. Okay, so but if temperature difference is there, definitely it will be there. So even though temperature difference is not there, okay, absorption and release will be there, but both will be same. So but emission alone is there mainly due to the temperature difference. Okay, note it down. Okay, shall I erase certain points? Okay, this is actually a slow process. This is a slow process. Convection is also a slow process. This is fast process. Okay, of the order of speed of light, we can say. We could say 3 into 10 raised to 8 meter per second rate. So almost of that speed radiations will be coming. Electromagnetic waves will be coming in this speed. Okay, light is also electromagnetic wave, right? Light is also an electromagnetic wave. Okay, fine. Then heat transfer here in this case is irregular path. This is also what? Irregular path. Okay, here in this case 4 4 4 5 5 5 straight line. Here this is straight line. Clear? Example, spoon dipped in hot soup. Okay, here example is trade wind. Okay, trade wind. What is trade wind? The wind that is happening between equator, pole, north, east. Okay, all these are because of convection. Radiation is example sun rays. Sun rays come to earth. Okay, this is example for radiation. Now this is a rough idea. We will move into the detail of this. Clear? Shall I erase this? Now we will discuss more about conduction. Okay, so what is conduction? Conduction is mainly what is happening when temperature to one side is more, then heat will be transferred from the end at high temperature to the end at low temperature. So how heat is transferred? Heat is transferred by the vibrational energy of atoms and molecules. Okay, so conduction is through the vibrational energy of atoms and molecules. Molecules are actually not shifting. So this is actually happening in solids. Okay, in solids what is happening? Conduction. So metals, iron, okay, steel, okay, aluminium, okay, silver, they are all good conductors of heat. We know conductors of electricity, good conductors of electricity, we know. Same way, good conductors of heat. Wood, we know wood. wood is not that good conductor, but it will conduct, but it is not that good conductor. So what we do, if we need to make a spoon which is safe, or if we don't want to burn our hands, we can make a wooden spoon. There are spoons like that. Okay, so the vessel will be what? Vessel will be that is in direct contact with the heat, right? So that one will be metal. It should conduct heat, then only we can cook. Okay, so that will be there, but spoon will be, if it is wooden, then it is comfortable. Okay, so good conductors, bad conductors of heat, everything is there. So conduction is mainly because of vibrational energy of atoms and molecules. Now in this, one thing which we need to study is, suppose if we take a conductor, that is heat conductor. Here suppose if we have kept, this is what TH means high temperature. TH means high temperature. Now if I maintain the other end at lower temperature, so I can say this is hot and this is cold, and if I am covering the full area, if I am covering this with the adiabatic walls, okay, adiabatic walls, if I am maintaining it inside adiabatic walls, then what will happen? There won't be any heat loss, correct or what? There won't be any heat loss. So suppose if this is a slab, okay, its length is L, and here the area is A. If the area is A, then what will happen? From the hot end, heat will be transferred to the cold end. From hot end, heat will be transferred to the cold end. Okay, so that Q, okay, that Q is what? Energy, okay, heat. So Q by T is called heat current. Okay, this is called heat current, which is nothing but heat transferred per unit time. Okay, heat transferred per unit time, Q by T. This is equal to Ka by L Th minus Tc. Okay, Ka by L Th minus Tc. What about this K? K is called thermal conductivity. Thermal conductivity. Okay, so this depends on the material. Certain materials will be having good conductivity of good thermal conductivity. Certain materials will have bad thermal conductivity. Okay, so heat current is equal to Ka by L Th minus Tc. Clear? Now obviously this one is what? Joule. This is joules per second. Okay, joules per second. And if this L come to this side, okay, we will find the dimensional formula now of K. So this one is ml square T raised to minus 2. This is the dimensional formula of Q. Okay, divided by T. This is equal to, let the K be here, and area we can put here L square, and this is divided by L, and this is what? Temperature. So temperature theta is also a fundamental unit, right? Out of 7 fundamental units, one is theta, so that is also a fundamental unit. Clear? So this L square can be cancelled off. So the dimensional formula of K is what? This T will go up, so M, this L will come this side, ML T raised to minus 3 theta raised to minus 1. So that is the dimensional formula of K. Note it down, please. Clear? Okay, its unit is joule, S raised to minus 1, M raised to minus 1, joule, S raised to minus 1, M raised to minus 1, K raised to minus 1. That is the unit of K, thermal conductivity. Clear? Okay, shall I erase this? Now we need to analyze this formula. Okay, suppose if we take a slab like this, okay, so at a distance x, if we consider a small distance, okay, if this small distance is dx, if this is at a high temperature and this end is at a low temperature, then again Q by T is equal to, here Ka, this area is A, fine, and here the heat current at this point is nothing but dt divided by dx, dt divided by dx. That is, if the temperature is given as a function of distance, then we will have to use this formula. Okay, Q by T is Ka, same thing only, instead of full length we are taking that small length, dt by dx. Okay, this also you can note it down. Fine. See, now this formula we can compare with the current in current electricity. This is heat current, general current IE is equal to what? That is also what? Q by T. This is equal to, we have studied like a voltage difference divided by resistance. Actually, voltage difference divided by resistance. So we shall elaborate this. So charge by time, this is equal to what? Higher voltage minus lower voltage divided by, instead of this resistance we can write rho L divided by A, because resistance is what? Rho L by A. Now again, I is equal to Q by T is equal to, this A can be put here, I am putting A here, this is VH minus VL divided by, instead of this rho is what? Reciprocal of conductivity. Rho is resistivity, this sigma is conductivity. So here what is this? This is thermal conductivity. Now here we will substitute with the electrical conductivity. So sigma A divided by L. So now this both are having same structure. Both are having same structure, you can see. Okay, Ka by L, this one is sigma A by L. This is potential difference, that is temperature difference. Clear or what? Okay, so what is resistance here? What is resistance here? Here in this case the resistance is what? L by rho A is the resistance. So here we can say the thermal resistance R will be how much? This is actually L by Ka. L by Ka. So similarity is there. Okay, lot of similarity is there. Okay, both are similar, so we can take this analogy. Clear? Shall I erase this? Note it down. Fine. So because of this similarity, even this resistance in series, resistance in parallel, that pattern also same in both. So just like two resistances R1 R2, R equivalent is what? R plus R2, R1 plus R2. So this R1 will be what? Sigma A by L. So sigma A divided by L1 plus sigma 2. Both are two different resistances. This is R1, this is R2. Both are different resistances. So sigma A divided by L1 plus sigma A divided by L2. Likewise, this is how it is going to come. Now suppose if you keep two slabs, okay, their areas are same. Okay, the length is L1, L2, its thermal conductivity is K1, its thermal conductivity is K2. Then here the R is going to be what? R1 plus R2 in this case also. So R is equal to, what is resistance? L by, so L1 by K1A plus L2 by K2A. Okay, so here what about this resistance, this side? This side it is going to be if total resistance L1 plus L2 divided by this K equivalent, we can take K equivalent into A is equal to, okay, so this is equal to, we will substitute this L1 divided by K1A plus L2 divided by K2A. Correct or what? So from this A can be cancelled off. If I bring this K equivalent here, K equivalent if I bring here, this is going to be L1 plus L2 divided by L1 by K1 plus L2 by K2. Okay, so this is the equivalent thermal conductivity. So even resistance also can be asked. Directly resistance also can be asked. Certain previous year questions are much easier than this. Directly we will be able to tell. So if the resistances are connected in parallel, we know how to take its result. Same way, if we have taken two slabs, its area of cross section is A1, its area of cross section is A2, and the lengths will be common. This is at a higher temperature, this is at a lower temperature, then heat current will be, or heat will be flowing in this direction. So in that case 1 by R equivalent is equal to 1 by R1 plus 1 by R2. That is what we are going to do here. So if R resistance, thermal resistance is L by Ka, if we take its reciprocal, this is going to be K divided by L. Instead of area, we will have to take A1 plus A2. So A1 plus A2. So this is equal to, this is K equivalent, okay, equivalent. So this is equal to K1, its thermal conductivity is K2. So K1 A1 by L plus K2 A2 divided by L. So L if we cancel, then K equivalent is going to be what? K1 A1 plus K2 A2 divided by A1 plus A2. So this is the K equivalent. So based on the situations we can do. Okay, just for your understanding I said this. Clear? Note it down. Pause the screen and note it down. Now in conduction, or just an application of a conduction, or we can say a natural example which we can see, the effect of conduction is the formation of ice in lakes and ponds, okay, in cold regions. Okay, suppose formation of ice, okay, formation of ice in ponds, okay, or lakes. Suppose if this is a water body, if this atmospheric temperature, if atmospheric temperature is less than 0 degree Celsius, obviously ice formation will be there. And in anomalous, while discussing anomalous expansion of water, we know at the bottom there will be water, okay. So at the top less dense ice will be there, okay. Water at 4 degrees Celsius will be denser, okay. So fine, suppose if we consider here, this is formation of ice, okay, this is formation of ice, okay. Okay, so if we consider this is, okay, a pond. Suppose if you know, okay, we have taken, so this much is ice, okay, already formation of ice has happened. Here the atmospheric temperature is minus theta degree Celsius. Here the temperature is minus theta degree Celsius, and wherever water is there, there the temperature is going to be 0 degree Celsius, okay, where just after, just below the surface of ice, okay, 0 degree Celsius water will be there. Now another, suppose if we consider this is the ice which is forming now, okay, how it is formed, how much time it will take, okay, let us consider. Now what will happen, conduction is what, heat will flow from higher temperature region to lower temperature region. So what will happen from here, this is at a higher temperature, we can say this is at a higher temperature and this is at a lower temperature. So what will happen, heat will be flowing in this direction. So in calorimetry we have studied, when heat is extracted, what will happen there, either temperature will be decreased or phase change will happen. In what direction? Steam to water, water to ice, in the backward direction. So since heat is moving in this direction, there will be formation of ice here, okay. So let us see, what is heat current? Q by T. Q by T, okay, is equal to what? K A divided by L TH minus TC. This is the formula. Now the change in the flow of heat, if we consider like dq by dt, this is equal to what? K A divided by, what about this? This is length. So suppose if the formation of ice is for dx length, let us consider this as dx, and this is what? This is TH minus TC. So higher temperature is 0 minus lower temperature is minus theta degrees Celsius. So minus theta. Is it clear? Now what about this heat? What is happening with this heat? When this heat is released, ice formation will happen. So we can say this heat is released by formation of ice, or when this heat is released, formation of ice will happen. What is the energy required for the formation of ice? We can I write ml, latent heat of fusion mass, divided by dt is equal to Ka, okay, divided by dx into theta. Now what about mass? Mass is equal to volume into density. So mass of this segment, mass of this one, so this mass is equal to what? Volume into density, or we can say area. This is area into its thickness is how much? Dx into rho. So I will substitute there A dx rho, okay, volume into density, yes, okay, into L divided by dt is equal to Ka. Okay, here I have taken dx. Actually, how much is there? Suppose if we consider this length as x, the extra formation is just dx. So here instead of dx I am taking x, because this thickness we need to consider, correct or what? When we consider a slab, this is the length, that length is what is this, so this length we need to consider. So I put here dx, that is wrong, I am making it as x. Okay, so Ka by x into theta. So I can cancel a I can cancel. Now dt is equal to, okay, so dt is equal to, x will come to this, dt will go to that side, so dt is equal to rho L divided by k theta, rho L, that k theta will come this side, dt went to that side, okay, into x dx. Okay, so note down till this, I am going to erase that. Okay, note down, I am going to erase that. We need to find the time taken for the formation of ice. Okay, shall I erase this? Okay. Okay, so now dt is equal to what? Dt is equal to rho L divided by k theta into x dx. Now if I need to find the time, to make a thickness, okay, from 0 to x or x1 to x2, everything we will see. So t is equal to what? Okay, t is equal to integral dt from 0 to t. This is equal to rho L divided by k theta, integral from what thickness to what thickness? Okay, say from 0 to x. Okay, suppose if the thickness is 0, okay, then to make a thickness of x, how much time it will take? That is what we are going to find. So t is equal to what? Rho L divided by k theta x square by 2, 0 to x. So what we will be getting? The time taken for getting a thickness of x will be 1 by 2 rho L divided by k theta into x square. Okay, so in order to get a thickness of x, time taken is nothing but half rho L k theta into that thickness square. Fine, clear? Okay, so nothing. Here the temperature is less, here the temperature is more. So heat will flow in this direction. So what will happen when heat is extracted? Here the change of state is happening. So change of state, the formula is nothing but ml. Okay, so this thickness is considered in the formula, and the if we assume that a ds thickness or a into dx volume is formed, okay, assuming that we put ml there, then we just integrated, we are getting this answer. Okay, shall I erase this? Okay, so suppose already a thickness is there, x1 thickness is there already. So from x1 thickness to x2 thickness, how much time it will take? So nothing but t is equal to, we will change the limit here, that's it, no other change, rho L by k theta, integral from where to where? From x1 to x2 x dx. So t is equal to here rho L by k theta x square by 2, putting the limit x1 to x2. So the time taken for changing the thickness from x1 to x2 is half rho L divided by k theta. Here this is going to be x2 square minus x1 square. Okay, so this also you can note. Okay, clear? So t is proportional to what? T is proportional to x square. So suppose if we need to find the ratio, okay, please note it down, we will write that also. Okay, shall I erase this? So time taken to double and triple the thickness, time taken to double and triple the thickness. Okay, already a thickness is there, so time taken to double and triple the thickness, T1 is to T1, T2 is to T3. Okay, so this will be 1 square is to 2 square is to 3 square. Okay, so this is T is proportional to x square, so T1 is 2, T2 is 2, T3 is what? 1 is to 4 is to 9. Okay, not that also. Okay, so this is about conduction. Okay, okay, so next type of heat transfer is actually convection. Okay, so convection is through the real movement of molecules will happen. Okay, so this is just like say for example here we will consider this spot and this spot. So here suppose the density is less. Here if we increase the temperature, the density is less. Here density is more. Okay, here the density is less, here the density is more. How it is made? Just if we increase the temperature of this area, what will happen? Obviously this density will come down. So what will happen? Here these molecules will come to this side, this will mix, and finally it will try to attain thermal equilibrium. Okay, so this is the process of convection. Okay, so lot of natural examples we have with this method convection. I will give you few. Okay, so one example is like the wind from seaside towards the land and the wind from land towards the sea. This is an example of convection. Suppose if this is land, okay, this is land and this is ocean, okay, sea. So when sun rays fall on this land and sea, sun rays when it falls on land and sea, land will get hotter fast. Okay, this will become hot compared to this. The specific heat capacity of land is less compared to water. So what will happen? So this we are assuming daytime sun's rays. What will happen? Land will become hotter than sea. So during daytime what will happen? Here this is going to be hot compared to the water. So here the air molecules, what will happen to air molecules? Here the air molecules will have what kind of density? This is going to be, density will be less. Here air molecule density will be more. So what will happen? The air molecules will move from more dense area to less dense area. So wind direction will be in this way. This is the direction of wind. Okay, so this happens during daytime. Okay, clear? During daytime land will become hot first compared to water, okay, or sea. So the air molecules above land will become less dense. Okay, density will be less. Here compared to this, the density of air molecules will be more. So air molecules will be moving from more dense area to less dense area. So wind will be moving from sea to the land. Okay, this is happening during daytime. Now, so continuous exposure of sun rays, this sea water will become hotter when? In the evening. By evening, such a continuous exposure, okay, what will happen? during night this is hotter, and this land will get cooled down very fast. Okay, so this is cold. Okay, hotter and cold. So what will happen here? The density will be, so now this is more, the air molecules here, the air molecules here, the density will be less because it is hotter. Here density of air molecules will be, here this is going to be more. So in which direction wind will flow? So from more dense area, more denser point to ink. Okay children, fine. So this is more denser, so air will move from more dense area to less dense area. So during night time the wind movement will be from land to sea. During daytime the wind movement will be from sea to land. Okay, so this is a natural example. Trade wind is another example. Trade wind, because the equatorial side, because of because of high temperature, the density of air will be less. Polar side, the density of air will be more. So wind will be moving from pole to equator in lower area, and upper area wind will be moving from equator to pole. So likewise trade winds are there, monsoon, all these are examples of convection. Okay, is it clear? Please note it down. Okay, dear students, so we have covered conduction and convection. Now we have radiation also. Problems also will come from this area. We will see that also in another session. Okay, goodbye, good luck.